The title of the course is Probabilistic Method in PD. In this course, what we are going to do is we are going to see the fundamental basic tools of probability. Mostly those are stochastic processes and stochastic calculus, and then we are going to see how those would be used to solve some PD problem. So, for that I am going to use a particular book mostly, that is the Brownian motion and stochastic calculus by Karajas and Shreve. There will be another book that is on semigroup theory written by A. Pazzi. More than half of the course would be based on few chapters of this book. However, I would not start from the very beginning of the book, because the beginning is dedicated on stochastic process, some fundamental basic things. I would be rather little fast on first few chapters. I would like to keep this course as self-contained as much as possible. Okay, so let me open the first slide. In the first slide, we are going to see what we mean by random variable. That is the first thing we start for in a course in probability theory. So, what is a random variable? When we ask this question in a statistics course, the answer is result of a random experiment, outcome of a random experiment. However, when we talk about the mathematical probability theory, then we take the mathematical model of this random variable. Okay. So, random variable is of course outcome of a random experiment, but instead of modeling what is random experiment mathematically, we just model this outcome as a measurable function in a probability measure space. So, for our course, whenever we say that x is a random variable, we mean x is a measurable function defined on a probability space. So, let us start with some very simple example. If I say, so this example is saying that x, and this symbol is denoting the follows, that means x as a distribution u, and then a set containing only two elements 0 and 1. So, what is this u denoting? U denotes uniform. So, I mean here x is a random variable which follows uniform distribution on the binary set 0 and 1. That means that it has equal probabilities at point 0 and point 1, or in other words, x is a random variable which takes value 0 with probability half and 1 with probability half. Okay. So, this is distributional description of a random variable. Okay. And that type of random variable you can find in nature, say for example, tossing an unbiased coin. Okay. And head stands for 1 and tail stands for 0, then you can actually replicate such random variable. But how can we mathematically model that random variable? So, let us see how are we modeling that random variable mathematically. We are taking a function x from interval 0 1 to the set binary set 0 and 1. Okay. Left hand side you have the closed interval 0 and right hand side you have binary set 0 and 1, and this is given by this function is x of omega is equal to indicator function of the interval 0 to half, and this indicator function evaluated at omega. Okay. So, now right hand side takes only two values 1 and 0. It takes value 1 when omega is inside the interval 0 and half, and it takes value 0 when omega is outside this interval 0 and half, correct. Then this indicator function gives you 0. So, here precisely this x, okay, is a candidate for this example, but let us see whether this really puts half of probabilities for 0 and 1. For that we need to mention what are the weights and what is the probability. So, here we specify that the probability space. Now, we are specifying. So, 0 1 interval is the non-empty set. On that we are considering the sigma algebra, Borel sigma algebra on closed 0 1. Okay. And M stands for the Lebesgue measure. Okay. M stands for the Lebesgue measure. So, now this is a measure space. Okay. and then total measure of the set 0 1 is 1, because Lebesgue measure of 0 1 interval, the length is just 1. So, measure is 1. So, it is a finite measure space where total measure of the set is 1. So, it is a probability space. Okay. So, by saying that, I am also recollecting the definition of probability measure. So, here we have a probability measure space, and we have a function x defined on 0 1 this way, and this function is of course a Borel measurable function. Why is it so? Because it is indicator function of a Borel set. Closed interval 0 to half is a Borel set. So, this random variable, this measurable for this function is measurable with respect to the measure space this. Okay. So, here as I have noted, what is my random variable is nothing but a measurable function. So, x is really a measurable function here. Now, we calculate the probabilities. What is the probability that x is 0? Okay. What is the probability that x is 0? So, for that we are going to find out the measure of the set of omega where x becomes 0. That is nothing but complement of 0 to half inside this 0 1. So, that is open half closed 1, that has measure Lebesgue measure half. Okay. The length is half. So, probability x is equal to 0 is half here. Okay. So, this actually proves that the construction what we have done x here is indeed a random variable whose distribution uniform on 0 1. Now, this random variable has a popular name among statisticians, we call that Bernoulli trial. Okay. So, let us consider another function y. One can say that okay, can we have another measurable function having the same distribution? The answer is of course yes, there are actually plenty of such. So, this is only one another example. Y, it is defined as 1 minus x. So, 1 minus x is indicator function of, here there is a mistake, here it should be open half 1 closed. Okay. So, that random variable follows uniform 0 1 again, okay, due to the same reason. So, here x and y are two different measurable functions, and however, they are equal in distribution. Okay. Fine. Now, we go for little more details of some other random variables. Okay. I mean we are taking normal random variable. So, earlier it was Bernoulli trial, which is a discrete random variable. Now, we are going to talk about normal random variable, which is a contrast random variable, and this example I would consider to illustrate two other different ways to find out two different way of modeling a given random variable. Okay. So, here this symbol says the x has a distribution which follows normal random variable 0 1, that we mean 0 and variance 1. We consider the probability space the real number, set of real numbers, Borel's sigma algebra on R, and mu a measure which is defined following way. Mu of set A, where A is a Borel set, is defined as integration over the set A of this integrand. Okay. This integrand is 1 over square root 2 pi e to the minus x square by 2 dx. Okay. Now, if we consider this measure space, we can ask that is it a probability space? Yes, because mu measure of the whole R is integration of this function over whole R, and that integration is 1. So, it is a probability space. Now, question is that what should be my random variable, correct? So, what should be my that measurable function, so that under this probability space it is normal random variable with mean 0 variance 1. Okay. So, here we do that, we take x of omega is equal to omega, just identity function, and then the probability of x belongs to A, this is equal to, therefore, mu of, because the probability is now for us mu here. So, this is nothing but mu that of omega such that omega is in A, because x omega is omega here, but that is nothing but mu of A, which implies that this probability density function of this random variable is this, because mu of a is this right hand side is nothing but this integration. Left hand side I have probability x belongs to a, right hand side I have integration of a function on the set A. So, this left hand side I have a here, right hand side I have a here. So, that implies that the probability density function of x should be this integrand. So, what does it mean? It means that capital X is normal random variable, because we know that this function is the probability density function of standard normal random variable. So, this proves that this particular choice of measurable function and this particular choice of probability space together can model a normal random distribution, standard normal distribution. So, we go to the next slide. Now, as I have promised, now I am showing another way of modeling standard normal distribution. Earlier what we have done, we have taken a very canonical choice of random variable, just identity function. So, we have not included any information in that. Okay. However, all the normal random variables for the normal random variable, whatever the distributions information, that we have encoded in the measure itself. But here another complementary manner. Here we take a very flat standard measure space, closed 0 1 interval, Borel sigma algebra on 0 1 and the Lebesgue measure. So, that means this choice of measure space is not incorporating any information on the normal random variable. However, we choose the measurable function here, so that it matches the normal distribution. Okay. So, this is taken as f inverse of y, for here it should be y. So, for all y for all y real, where here also it should be y. So, f of y is equal to minus infinity to y 1 over square root 2 pi e to the minus x square by 2 dx. Okay. So, we define this way. Then also we can prove that x follows normal random variable. How do we prove that? Because we just calculate the probability of capital X less than or equal to y. Okay. So, probability x less than or equal to y is same as, so now when I say x, I mean f inverse of y. So, sorry, here actually here it should be f in omega. Okay. So, here omega, but here y. Okay. There is a, so, f inverse of omega is less than or equal to y. That would imply that y is less than or equal to f of omega. Why? Because f here is a monotonic function, it is invertible. Okay. Probability x less than or equal to y is same as probability f inverse omega less than or equals to y. It is probability that omega less than or equals to f of y is equal to probability omega such that. So, what is f of y? F of y is, so I write down here clearly, set of all omega such that omega less than or equal to minus infinity to y 1 over square root 2 pi e to the minus x square by 2 dx. Okay. So, here p is nothing but the Lebesgue measure m, Lebesgue measure m. So, here it is m measure. So, Lebesgue measure of this set omega. So, here omega is between 0 to 1. So, omega is between 0 to 1. So, here we want to find out the Lebesgue measure of that. So, it is nothing but Lebesgue measure of closed interval 0 to minus infinity to y 1 over square root 2 pi e to the minus x square d by 2 dx. So, this intervals Lebesgue measure, there is a length, but the length is exactly this value, because this is a positive number. Exactly this value, this is minus infinity to y 1 over square root 2 pi e to the minus x square by 2 dx. And what is this? Since this is the probability density function of normal random variable, So, this is nothing but the CDF of normal random variable. So, this f I mean this is that normal random variable CDF. So, here this was my x less than or equal to y. So, this is CDF of random number x. So, this matches. So, x has the same distribution of n is standard normal random variable. So, this is the proof that if I consider this pair, this particular probability space and this particular measurable function, then also I can model a normal random variable.